Okay, a quick note on the fact that the Fourier transform is a bijection while it's invertible. As you have already noted, we have defined the inverse Fourier transform, but we didn't really say anything about this. For the moment, what we know is that when your function belongs to L1, we can define the corresponding Fourier transform of your function. Now, what about L2? So let us first prove that if that the Fourier transform, so which I will abbreviate with ft, is injective in L2. Okay, let's see what we have. So you know that in order to prove injectivity, we assume that two arguments have the same value. Okay, so the Fourier transform assumes that the Fourier transform of f1 is equal to the Fourier transform of f2. How can we prove that then f1 is equal to f2? So what does that mean? It means that the integral on R of f1 minus f2 of x times the e minus 2I pi xi x dx is equal to 0. Okay, so that's what it means to have that the Fourier transform of f1 is equal to the Fourier transform of f2 by linearity. I just put that together. But then if you use the Parseval-Plancherel theorem, what do we get? We get that, well, we had that the Fourier transform, well, we've already written that, of f1 minus f2 is actually equal to the zero function. And by the Parseval-Plancherel theorem, I know that the norm of f1 minus f2 in L2 is equal to the norm of the corresponding Fourier transforms. So what does that give us? The norm of Fourier transform of f1 minus f2, okay, which of course is equal to 0 because it is because that's the zero function. That's our assumption. And so by the property of the norm, do you know that the norm of a function is equal to 0 if and only if this function is equal to 0? So that means that f1 is equal to f2. Okay, so if we have functions in L2 using that norm, that L2 norm, we have that is very natural using the Parseval-Plancherel theorem, we get that the Fourier transform is injective. But do we have that, and what about L1? Because we just said that it was L1. What about the Fourier transform in L1? Well, similarly, you can get that it's injective just using the convergence theorem by saying that, or using the inverse Fourier transform, for instance. You know that the inverse of the Fourier transform of f1 by definition is equal to f1 almost everywhere. Well, we could already have used that earlier, but that's then just comes from, if we've got functions in L2, then we can use the L2 norm. And here it's f2 almost everywhere, so if they are equal to each other, that means f1 is equal to f2 almost everywhere, and we've got injectivity in L1. Okay, the thing is that, do we have a bijection even though we have used the inverse function? What else do we need for the bijection? We need that the space it goes to, well, if I want a bijection in L1, I need something that goes from L1 to L1. If I want a bijection in L2, I need something that goes from L2 to L2. So in L2, that's natural from the Parseval theorem. Okay, tells you that the L2 norm of the Fourier transform is equal to the L2 norm of the function. So that means if your function is in L2, its Fourier transform is in L2 plus injectivity. So that makes it a bijection in L2. Okay, but in L1, the problem is that we have some example, for example, pi of x, our get function, which is obviously in L1. Okay, so that's my rectangular function. It's obviously in L1. And we saw that the Fourier transform of that was the sinc function, pi xi divided by pi xi. And if you want to compute the L1 norm of this function, so the value on or of, well, the integral or of absolute value of this, well, you see, it's not going to be in, it's not bounded. Well, yeah, there are many reasons why, but basically it's just going to be more or less equivalent to 1 over xi, and so that is unbounded. So the image does not belong to L1, but it, of course, it does belong to L2. So it's not what we can remember from that. It's not a bijection in L1, but in L2 it's the good space. So the problem is that we have defined the Fourier transform. At first we said we just need f to be in L1, and you know there is no inclusion between the spaces. Well, there's a whole stuff that tells you that we're going to approximate L2 functions by functions that belong to, I'm just citing that for the amendment. For your culture, we will use that maybe a bit later. We're going to talk about the Schwartz space, which is the space of infinitely differentiable and fast decreasing function. So all the good functions, infinitely differentiable plus fast decreasing at infinity, which are functions that can be used to approximate anything in L2. So in that Schwartz space, S of R, everything goes fine, and you can define, of course, your bijection very well, and then you get the L2. You can approximate any function from L2 from that, so it's still working there. And we get that actually S of R is dense in L2. So that is what's used for the approximation. And finally, just as a side note, because we studied that last year, we have that the Fourier transform is a bijection in L2, plus the fact that the norm 2 of f is equal to the norm 2 of its Fourier transform. That's Parseval-Plancherel theorem. So you remember that's how we call Parseval-Plancherel theorem. You remember that's what that defines something called an isometry. Okay, plus it's linear, so it's a linear isometry of L2. Good.